Okay, amazing. Yeah, so hey everyone, I'm Siddharth, and yes, I'll be talking to you about a fairly long title, which is indeed about decision procedures for bitvectors whose widths are arbitrary. So yeah, let's begin. But first, these are my lovely co-authors. There's Leo, there's Chris, and there's Tobias, and it's been a lot of fun writing the paper with them. And so, right. So maybe to set some context, right, like why do we care about this stuff? So essentially, the area that I work in is compiler verification. And we're interested to know, are these two programs equivalent, right? Do they have the same semantics? So, what the source program, it divides by 8192, and the target program, it shifts right by 13. So if you remember your powers of 2 to the 13 is 8192, so these two programs do indeed compute the same value. But, how would you verify this if you're an LLVM developer, for example? What you'll do really is to just invoke a tool called alive, which is written by actually some of the people are actually attending here. I've seen Nuno here for sure. And yeah, so alive is a really nice tool where you feed it the source and target program, and then alive tells you, hey, look, this transformation seems to be correct. Like this is in fact a legit transformation to do. Now let's suppose instead you screwed up when you wrote a compiler pass that converts division by 1 into shift right by 13. This is of course wrong. And if you ask alive this, alive will indeed say that, hey, this looks illegal. It says, on this input, which is when you give it as input 1, the source program produces as output 1, and the target program produces as output 0, right? And so, I mean, this is super fantastic, right? Because when you're developing a compiler, a large portion of the compiler's optimizer has these peephole rewrites. So it's really important to get them right. And essentially, alive is used pervasively within LLVM development. So quite a few of the commits, or most of the commits to the sort of peephole optimizer in LLVM just reference the corresponding alive proof. This is not cherry picked, by the way. If you just go to the GitHub repo and you search for alive, you'll basically find hundreds to thousands of commits that do this. Yeah, so that's really awesome. So how does alive work? Well, roughly speaking, here's what it does. So it takes the two source and target programs. It converts them to a query to an SMT solver. If you've never seen this before, you can essentially think of this as some kind of logical language where the logical language knows about bitvectors. And it then ships this off to a solver, and it asks the solver, hey solver, you have these two functions called source and target. Do they always have the same output for all inputs? And I'm not going to really focus much on the translation from LLVM to the bitvector land. That in itself is fairly complicated because LLVM has crazy semantics about these things called undefined person. But instead, I'm mostly going to focus on how the solver actually solves this problem, right? So I'm going to focus on the latter part of the translation for today's talk. Right, but the solver really is a genie, right? In that, it's you ask it, hey, is this true? And it sort of tells you, right? So that's amazing. But I have one problem with this, which is it's kind of unfortunate that I need to say 32, right? Because this particular transformation that I have, it's legal really for any width that I want. So I really want to say, hey, please give me a symbolic width, and for this symbolic width, can you sort of verify this transformation, right? So sort of we want to take this bitvector solver that we have, and we want it to be a PBV solver, which is a parametric bitvector solver, or a width independent bitvector solver. So that's kind of the goal of this talk. We want to have a solver for bitvectors, but which not only reasons about a fixed width, which you can always convert into a SAT problem, but you want something that can reason about this parametric width as well. So sort of in our, in our implementation, we provide these two tactics within Lean. One is called BV automata, which is a solver for this thing, which uses automata theory. It's complete for a large fragment of bitvectors. And then we have another solver called BV MBA, which uses some algorithm that I will explain, which is cute. It's very fast, but it's only sound and complete for a much smaller fragment of bitvector problems. And of course, all of this is mechanized in Lean, so it's all available as tactics that you can use. Also, it's open source, and if you want to use the tactic, you can take a screenshot and you can include that link into your Lake file. So if you want to use the tactics, then that's how you use it. Right. So I'll now sort of get into the actual algorithms and how the sort of tactic works, and a little bit into the hard parts during mechanization. Right. So to set the stage, let's suppose we're trying to prove that bitwise AND is idempotent, which we know it is, and that's how you'd actually invoke our tactic. You'd say by BV automata, and then it gets proven. So okay, what does the tactic do? What does the actual decision procedure do? So the idea is, well, okay, we are trying to prove this identity for all possible widths. So we might as well imagine that the bit vector has infinite width, right? Because if you want to prove something for width 1 and width 2 for width 3, you might as well think to yourself, well, maybe I just prove it for the infinite width case, right? So now, you know, we have these two infinite streams, both of x and x, and then we look at x bitwise and x. So that gives us x0 and x0 at the first location, and then we try to check whether at that particular location x and x equals x, which it does, which you can sort of check by exhaustive enumeration. Okay, so at least for the first bit, we've established that the predicate we want to check is true. Great, then we progress to the second bit, where we again get the same kind of obligation, right? And then we again check that it's true. And so, you know, we can sort of keep going. So then what we've done is we've converted the question of checking that predicate for all possible widths into really the question as to whether does this predicate, when interpreted as a bitwise predicate, produce an infinite sequence of true, right? So that's sort of our reduction from this universally quantified bit vector thing into a bit stream semantics. So that's our first reduction. Now the second reduction is we take these bit stream semantics and we instead interpret them as automata. So let's maybe take a brief look at how we do this for bitwise AND. So, you know, let's suppose in our inputs, the input A has value 0 and the input B has value 1. Well, then the output needs to be 0, right? So that's what's written on the transition label there. These are finite state transducers, so they take two inputs and they produce one output. And then, you know, similarly we can sort of keep going. If the input is 1 and 1, then the output is 1, and if the input is 1 and 0, the output is 0, and so on, right? I think you see how it goes. So the transitions are labeled, and so when we transition, we label them by the output as well. So this automata essentially completely captures the behavior of bitwise AND given the input bits. So then the other operation that we need in order to verify x and x equals x is we then have an automata for the reading an input itself. So, you know, that automata is really simple. When it reads an input 1, it produces an output 1. And when it reads an input 0, it produces an output 0. And then what we do is we compose the two automata together. So, like, you know, you can compose finite automata together, where you can say, please take the input of this automata from this other automata. So we then compose the automata to get an automata for x bitwise and x, which you get by composing the a bitwise and b automata with the x automata. Cool. Now the next thing we need to be able to decide is equality of bit vectors. So for this we need a slightly more complex automaton, which I'll walk you through. So the idea is, well, we start with the state where we assume that, you know, things are good and that the bit vectors are equal. And now when we see the two bits are equal, we say true. And then, you know, we get the next two bits, which are maybe 0 and 0. We learn that it's true. But now what we see is we see a disagreement. A is 0 and B is 1. So we then output false and we transition to a sync state. Now the sync state will essentially always output false. And this is important, right? Because it's like once you know that at some width the bit vectors have begun to disagree, you then know that they will forever disagree for any extension. So that lets you transition to this state where you now always produce false. So it's like at this point we really have all the automata we need for the original predicate we were trying to decide for x and x, for equals and x. So we again play the same trick. We compose the automata into like the final automata we need, and that's what the automata looks like. And then we go back and we ask the question, right? Does this automata always produce true? Now we know by visual inspection that clearly the automata always produces true because there's no transition into the state that produces false. So in this case we can say yes, this automata does always produce true. And now sort of popping the stack a bit, well, what does this imply? This implies that the bit stream is always going to be true, but that essentially implies that the original goal that we were trying to prove is in fact true. So that's sort of the full sequence of reductions that we perform in order to prove what we were interested in. But, you know, I cheated a bit, right? Like here I said, yeah, okay, you know, just look at the automata and, you know, clearly it's true. But how do you actually convince a proof assistant of this? So essentially we have two different backends in order to do this. So we have one backend that does this based on symbolic model checking. So we use k-induction to do this, where we encode the automata as a SAT problem and we check for like that all reachable states are good. And we have another backend that's based on automatic structures, where we have a library for building NFAs, and yeah, like we do sort of automata minimization and then emptiness checking of the language to determine these. Yeah, and both of these are mechanized. So then, it's like, yeah, we can sort of like see that even operations like addition can also be encoded in this framework, right? You maintain one state, which is your carry, and that tells you what you need to do. And then similarly, in the exact same way we encoded bitwise, and we can also encode predicates, right? Like we can take the conjunction of predicates, and we can take the disjunction of predicates, and so on in the same way. So basically, a lot of stuff is automata representable, in that like the full linear fragment along with Boolean combinations of predicates and things like this, right? So then let me explain the second algorithm, which works on a fragment called mixed Boolean arithmetic. So this fragment has on the inside bitwise terms and on the outside linear arithmetic terms. So it's a stratified syntax. So that's the sort of formal syntax, but I think you get the idea. So the way we actually prove this is we first show that this relation holds for bitvec1. So what I mean by that is when we substitute 0, 0, it evaluates to 0. When we substitute 1, 0, it evaluates to 0. Similarly for 0, 1. And crucially for 1, 1, we get 1 plus 1 minus 2. So this algebra is happening over the integers, not on the booleans. So once we know this fact, we can then lift it to any number of bits we want. Because if we take a 2-bit number and we interpret that number over the integers, what we wind up getting is this kind of expression, where x1, x0 as bits becomes 2x1 plus x0 as integers. And so then we can grab all the first place digits, rearrange the terms, which is equal to 0 by the theorem we proved before. And then we can also grab the lower bits, which is once again equal to 0 by the theorem we proved above. So this somehow lets us lift the result in bitvec1 to any bitvec w. How well do these solvers do? Well, we tested it on 2 problem sets. So one is on this MBA-Blast problem set that comes from deobfuscation. So as you can see, the sort of the MBA solver, which is specialized, like is really good on this data set. And yeah, the automata solver solves all of them. The k-induction solver solves up to 1500, and after that, the sort of how to say, the SAT formula get really large, so it times out. In terms of compiler verification, we take the rewrites from LLVM, and essentially, like on the 8,000 problems, we can solve something like 2,300 of them. Of the ones that we don't, it's either because these rewrites in LLVM are fixed to 64 bits, so they involve numeric constants that we need to first generalize, which we haven't done yet. And also there are some rewrites which involve multiple widths and 0 and sign extents between these widths, but our solver assumes that everything has the same width. And finally, there are rewrites that are just outside of our fragment because they involve operations like multiplication and division and so on. But yeah, so I guess that's what I'd like to say. If you can use our solvers to trust your rewrites with formally verified solvers. So I can promise our solvers has no bugs because it's written in lean, and it's pretty fast as well. And so yeah, there's the Git URL to actually grab the solver. And finally, I'm trying to figure out what I do with my life after my PhD. So if you have advice or positions, please hit me up. Thank you. Yeah.
Please, question.
Thanks for the really interesting talk. One thing that these kind of automata-based solvers can do that is deal with quantifier alternation. And so I'm curious if you've seen any examples like an LLVM where quantifier alternation might actually be useful, or is it just generally what we care about really is just for all statements?
Yeah, so that's a good question. So like there's a paper from last year called Hydra, where the idea is that they take a bitvector rewrite that involves 64 bits and then try to shrink it down to like 4 bits. This is like a step that you need to do in their larger algorithm. And to do this, you need an exists for all quantifier alternation. So that like it is in fact useful. And yeah, you're right that we could in fact do quantifier elimination within our thing, although we haven't implemented it yet. But that's one use case where it would genuinely be useful. Yeah.
Cool. Thanks so much.
Yeah.
I have a similar kind of question. So your decision procedure generalizes to symbolic finite combinator.
Yeah.
What would be the sort of use case for Bitvector problems that need those criteria? Like what would they look like?
Sorry, could you clarify? Like,
what are some examples of Bitvector
So like I mean, so maybe this wasn't really clear, but in some sense it's like the way in which we sort of handle the Boolean fragment, like the full predicate combination, is by building individual automata for each of the atomic predicates and then combining them symbolically with the with sort of intersection and union of the languages. So we somehow like fundamentally make use of the fact that regular languages are closed under complementation and intersection and union.
So by symbolic finite automata, I mean finite automata where the transition labels.
Yeah,
Unary
exactly.
predicates.
Yeah.
Maybe I can ask you offline.
Yeah, that's,
okay.
that's
see,
what I wanted to
maybe we can-
suggest.
yeah.
All right. Well, thank you again.
Oh, thank you.
And